So let's take a closer look at our problem. It's going to be a problem about correlation. As we can see there, linear association would be a synonym, and simple linear regression. So researchers investigate the linear association between a semester score, a semester test score, and then the final grade of students. They collect data on 100 random students from a university. And then the data consists of these 100 observations for these two variables. Now remember, they are both ratio type. They both have a ratio type level of measurement. So there's a nice little plot of the data. It's a scatter plot, of course. We see the semester score on the horizontal axis. We see final score on the vertical axis. And first of all, visually, very easy to see that there'll be positive correlation as semester score increases. So does final exam score. And it seems to be fairly strong linear association or correlation there. The table below shows results of their values. So n, the sample size, would be 100. We see an intercept estimate, 39.7398, an intercept standard error of 1924. That is 1.924. A slope estimate of 0.4937. The standard error for that slope being 0.0024. The sum of squares total, remember that's summing over all the squared differences between the actual response variable value and the mean. We see that as 4106.74. The SSR, the sum of squares due to the regression, remember that's summing over the square differences over what our model estimates the value to be for y, the response variable, and the mean. We do not see the sum of squared errors there due to the residual, because it's easy to calculate from the SST and SSR, and we see a Pearson's correlation coefficient of 0.8982, 89.82%. That's very good, and visually we saw that as a strong positive correlation. So we're going to have to do the following four problems, and we are going to assume in all cases that the assumptions for the use of our tests are met. And so the first one would be determine if the correlation coefficient, that's R, is sufficiently different from 0 at the 5% level of significance. We have to write the equation of the simple linear regression model that uses semester score as the explanatory variable and the final score as response variable. We have to determine if the slope estimate is significantly different from 0 at the 5% level of significance. We know that to mean for this model with a single explanatory variable if the data is or at least the semester score is a good indicator of final score, and then use an F-test or analysis of variance to evaluate the simple linear regression model. So here we go on my piece of paper. As always, I've just rewritten everything we've been given, and instead of saying in the estimate of the intercept, remember that's beta sub 0 hat, and then the slope estimate beta sub 1 hat, the two standard errors for that. So let's start then with the first problem. Let's say problem 1. Let's say the problem 1. And so let's do all the steps. Step number 0 is everything we need. Step number 0, we're just going to summarize everything. Now, we've gotten most of what we want. We just have to remember that for this test, it's going to be a t-test for this correlation coefficient. What we need for that test, of course, we need R. We need a value under the null hypothesis, and we were given that in the problem. And we need our sample size 100 there, so we've actually got already all of that done. So let's move on to step number 1. So in step number 1, we know what is the population parameter that we are interested in. That is rho, that funny looking P, the population correlation coefficient, the population correlation coefficient. Let's go to step number 2. Step number 2 is we want the null and alternative hypothesis. Under the null hypothesis, this rho is going to equal 0. And under the alternative hypothesis, the correlation coefficient is not going to equal to 0. The question just said, is it significantly different from 0? So we're going to use this two-tailed test. Step number 3 is our level of significance. And remember, we were told at the 5% level of significance, so alpha is 0.05. Step number 4, what test are we going to use? And all the assumptions. Now we were told that the assumptions are met. And the test that we are going to use is the Pearson product moment correlation test. That is a t-test. And then let's do step number 5. Now we've got to write down, let's do that in green. So we're going to write that t, our t-statistic, remember that is our correlation coefficient minus what we think under the null hypothesis, that was just 0. And then we're going to divide that by its standard error, and the standard error is going to be 1 minus r squared divided by n minus 2. And remember, this is going to be described by, if I were to do this t over and over and over again from a population in which there was no correlation between these two variables, that will be distributed by a t-distribution, and a single parameter is the degrees of freedom, and the degrees of freedom is going to be n minus 2, so that's 100 minus 2 is 98. So let's look at that. Let's fill in some values. So the t-statistic is going to be, we have for r 0.8982, and we're going to divide that by the square root of 1 minus 0.8982 squared divided by n minus 2, that's 100 minus 2. So let's get our calculator out and do that. So t is going to equal, so here's my old phone that I have all these calculators downloaded on. Let's have 0.8982. We're going to divide that by the square root, and let's put that in parentheses. It's 1 minus. We're going to have 0.8982 squared. And let's move outside of those parentheses because we want to divide by 100 minus 2. And if we get that solution, we see that's a very big t-statistic. That's going to be 20.227. So we've got our t-statistic. We can now go on and use our decision rules. So we've got step number 6. Let's go back in our calculator. Let's just go to the home button. Let's go down to distributions. I'm going to hit OK. And I'm going to scroll down to our friend the student's t distribution. Our degrees of freedom, remember we said that's 98. It's n minus 2. N was 100 minus 2 is 98. So I want 98 degrees of freedom. Let's hit next. Now I'm just going to go to the left button right over there. Hit OK. For the critical value, I want the positive or upper-tailed one, so I'm going to go down to the bottom. And then I'm going to scroll across because I want the top 0.025 of that curve, 0.025, that's alpha divided by 2. And if I hit OK, I see my value there. That's going to be the critical value. Now remember that x is just a placeholder. So that should actually be t, but this calculator is always just going to put an x there no matter what our statistic is there. So it's going to be, if I'm at that little spot right there, 1.984467, that is going to represent this upper 0.025. That is 2.5% of the area under the curve. It's a two-tail alternative hypothesis. My alpha value is 0.05, so I've got to have 2.5% here at the lower tail, 2.5 at the upper tail, and right there at 1.98. That's where I would get that. So that's going to be my critical value. So let's put that in. So the t critical value, that is going to be 1.98, let's make it 1.984, 1.984. And we have that our t statistic is much larger than the critical value. Now do remember our t statistic is positive in this case. But what we really always want to do is we want the t, the absolute value of t, so for instance t was negative, if that is more than t crit, and then the critical value, remember we always take this upper tail. And so we're going to reject the null hypothesis, and we accept the alternative hypothesis. So in this case, I'm not going to bother with a p-value. We can just stick to this one decision rule. We've rejected the null hypothesis. So let's go to step number 7. A test conclusion, we're going to say there's enough evidence in the data at the 5% level of significance to show that the population correlation coefficient is not 0. So we're going to say that these two variables are correlated. Great, let's go to problem number 2. So now we've got to write down this equation, and the equation we're just going to say that we estimate, I'm going to use y for my response variable, we're going to estimate, so put a little hat on, for every single person, we're going to estimate their final test score, and that is going to be, remember, this estimate of the intercept, and so that's the estimate plus the slope estimate, and let's put just x, some value x for our semester grade, and I'm going to put a little I there, so that's for that specific person. So we're going to say we're going to estimate this value, the response variable value, and for beta sub 0, we're going to put in the estimate slope, and remember that's what it was, 39.7398 plus our beta sub 1, 0.4937 times whatever value we plug in for that semester score. So that's the mathematical notation as far as just using the estimates are concerned. So let's look at problem number 3. So problem number 3 says determine if the slope estimate, that's beta sub 1 hat, is significantly different from 0 at the 5% level of significance. So let's do step number 0. We've got most of what we want. Step number 0, we've got most of what we want. We're going to use, again, a t-statistic. And the t-statistic is going to be easy to calculate because we have beta sub 1 and we have its standard error. We just need to know what the degrees of freedom are. So let's put that in here. The degrees of freedom that we are going to use here, it's going to be n minus k. Now, let's have a look at what k is here. K is going to be 2. I've got two parameters, beta sub 0, beta sub 1. And I have n as 100, so 100 minus 2 is, I'm going to use the t-statistic on 98 degrees of freedom. So let's look at step number 1. What is our population parameter? Well, that's going to be beta sub 1. That is the population slope. For every 1 unit increase in my explanatory variable, by how much is the mean of my response variable going to change? Let's look at step number 2. Step number 2, the null hypothesis. It said significantly different from 0, so in the population we're going to say that that slope is 0. And then alternative hypothesis that beta sub 1 is not equal to 0. Step number 3 is very easy. We were told using level of significance of 5%. Step number 4, well, we're going to use a t-test. And we are told the assumptions for the use of this test are met. And so we're going to say step number 5, let's write down the t-statistic. And remember our t-statistic here, that is just going to be beta sub 1 hat. And we're going to divide that by, let's try and do it at least neatly. We're going to divide that by the standard error of beta sub 1 hat. And that's going to be described by the t-distribution on, we said, 98 degrees of freedom. And remember, as before, I should have just written under the null hypothesis, So if we want to calculate that quickly, let's put that all here while we still have a little bit of space left. T is going to equal beta sub 1 hat. So let's have beta sub 1 hat. Remember that was that, 0.49, 0.4937, and we're going to divide it by its standard error. There we go, we had beta sub 1 hat, 0.3, and then that was, the standard error was 0.0024, and let's see what that gives us. Let's get our calculator in. Let's go to calculations at the top, and let's do 0.494937, and we're going to divide that by 0.0024, and we get a very large t-statistic of 205.708, and that is, of course, it's going to be way bigger than our critical value. Let's do our critical value. So step number 6, of course, that's our decision rules. Let's just use a critical value approach so we can calculate the critical value. And so let's use our calculator for that. We're going to go down to distributions. We're going to go down to a t-distribution. In our degrees of freedom, remember we did that before, that is 98 degrees of freedom. N minus k, or 100 minus 2. We have two parameters in our model. I'm going to click on OK. And once again, I want that upper tail. So I've got my critical value there, 1.98. 1.98. Let's have 4. And so we have that our absolute value, the absolute value of our statistic, now it is positive, so that's fine. It is larger than the critical value, and hence we're going to reject our null hypothesis and we accept our alternative hypothesis. So our conclusion, so I've written there's enough evidence in the data at the 5% level of significance to show that the semester score is linearly associated with the final test score. And now you can go back in some extra credit, I suppose. You can then say for every 1 unit increase in the semester score, this final test score increases by 0.4937. Next up, let's do problem 4. And in step 4, we want to do analysis of variance on F-test. Now we're going to do this as an exercise, but remember the F-test, this analysis of variance on our linear regression model, we're going to do that if we have more than one explanatory variable. Because we want to evaluate the model as a whole. But we only have a single explanatory variable, and we've already shown that it is linearly associated with the outcome. And so we are done. We can really just interpret that. If we had more than just a single explanatory variable, then we want to assess the model as a whole using analysis of variance with an F-test. And then we can look at those individual slopes. But let's do that here just for an exercise. For step number 0, let's just see what we need, what we don't have. One of the things that we don't have is the SSE, the sum of squares due to the error. And that's easy to do because the SSE plus the SSR must give me the SST. So let's go back home, let's go back to our calculations, and let's have a look at that. Let's calculate the SST, or the SSE. So that is going to be the SST, which was 4106.74 minus the SSR, which was 320, 3240, I should say 3240.5145. That is 866.225. So let's go there. We have the SSE, which we definitely will need. That's step 0. 866.225. By the way, we're going to need nu 1. That's the numerator degrees of freedom. Remember, that's k minus 1, and we do have that k is 2. We have two parameters in our model. 2 minus 1 is 1. If we look at the denominator degrees of freedom, that's n minus k. That's going to be 100 minus 2. That's 98. So we're going to have, let's just put it here, we're going to have this F statistic on 1 and 98 degrees of freedom. That's what we're going to have. So let's do step number 1. What is the population parameter that we're trying to look at here? And so we can say in step number 1 is that we are interested really in this predictive relationship between these two variables. And one of the way to look at that, express that, maybe as R squared. So let's put R squared there, coefficient of determination. In step number 2, let's write the null hypothesis. We could say that the R squared is 0. That means, there's no predictive relationship between X and Y. So let's put that out in Word. There's no predictive relationship. And then the alternative hypothesis is there is a. So let's do step number 3. The alpha value is 0.05. We were told that. Step number 4, well, we're going to do an F-test. We were told that the assumptions for the use of this test is met. Step number 5, let's calculate the F statistic. So let's write out what that is going to be. The F statistic is going to be the sum of squares due to the regression. And we're going to divide that by the numerator degrees of freedom. And we divide all of that by the sum of squares due to the error. And we divide all of that by nu sub 2. And that's going to be described by the F distribution, we said, under 1 and 98 degrees of freedom. And that is under the null hypothesis. So if the null hypothesis was true, and I would repeatedly sample from such a population, I would get a bunch of F values, and this is how they would be distributed. So let's calculate the F statistic here. So we need the SSR for that. Let's go have a look at what that was. There we go. The SSR was 3240.5145. That's going to be divided by 1. So I don't have to put that. Divided by 1, divided by the SSE, which is 866.225, divided by, oops, let's do that, divided by 98. And that gives us, let's have a look at the calculator. So let's have 3240.5145. We're going to divide that by, let's put inside our parentheses, 866.225 divided by 98. And let's have a look at that. That is a very big F statistic. That's going to be 366.61. Let's use our rules. Step number 6. Let's look at the critical value for F. So let's go back home. Let's go down to distributions, hit OK. Let's just go back. We want Fisher's F distribution. Our numerator degree of freedom was 1. Our denominator degree of freedom was 98. Let's click on next, OK. Now what I want is, of course, is the upper tail. So let's just go back there, hit OK. We want the upper tail part. And we want 0.05 on that upper tail. Let's hit OK. And there we go, right there at 3.94. At 3.94, that is our critical F value. And clearly, our F statistic is much larger than the critical value. And so we reject the null hypothesis. And we accept the alternative hypothesis. So let's write step 7. So I've written that there's enough evidence in the data at the 5% level of significance to show that the semester score does have predictive power in terms of the final score. There are many ways that you can write this. Remember, we're actually only going to use it when we have more than one explanatory variable to look at this model as a whole. Are these explanatory variables, are they linearly associated with our final score or our response variable? So what we can write here as far as these are concerned, remember that the population values that we are interested in, we could have also said that these are all the slopes. Now in this instance, we only have a single slope. So here we can say all slopes. Another way to have set this under the null is all slopes are 0 and at least one slope is not 0. So those would be the alternative ways. As a fun little exercise, we were not required to do this, but let's just look at the coefficient of determination, r squared, and that is going to be what proportion of the total sum of squares, the variability in my response variable, so SST, what proportion of that does my model explain? So let's have a look at that. Our SSR was 3240.5145. And we're going to divide that by the SST, which was 4106.74. And let's see what that is. Let's get our calculator out. Let's go back home. Let's go up to calculations there. Hit OK. And we want 3240.5145 divided by 4106.74. And we get 0.789. So we can say that's about 78.9%. We can say that our model explains 78.9% of the variability in the final test score.